Hi there. I hope you're having a great day. Today we are going to learn how to solve some limit problems that we could have taken a look at last time using tables and graphs, but this time we are going to look at similar types of problems by using algebraic methods. So algebra, I know there's some of you out there who just love algebra. Today's your day. You're going to get to use some of that algebra. And some of you are not such big fans of algebra, and that's okay too. But we are going to make use of some of those skills. So the first method that we will use under the heading algebraic methods is called direct substitution. Direct substitution is going to be the easiest method to solve a limit problem, but it won't work for any limit problem. If it does work, however, it's definitely the way to go. So for number one, we have the limit as x is approaching 6 of the function x plus 2 divided by the quantity x squared plus 5. Okay, so direct substitution means that you take that number 6 that x is approaching and directly substitute it in for the x's in the function. So this would equal 6 in place of this x plus 2 in the numerator divided by 6 in place of this x also squared plus 5. So my numerator 6 plus 2 is 8 and my denominator 6 squared is 36 plus 5 more gives me 41. That fraction is fully simplified. If it wasn't, we would simplify it. And there is our answer, 8 over 41. So, you know, you can almost think of this as like plug and chug kind of method. All you have to do is plug it in and work it out. So, take a look at number 2. Again, the limit as x is approaching 6. This time our function is x cubed plus the square root of the quantity x plus 5. So, we're just going to substitute 6 in place of the x, so it'll be 6 cubed plus the square root of 6 plus 5. And 6 cubed is 216, so 216 plus the square root of 11. And 11 doesn't have any square factors. It's a prime number, so that's as simplified as the answer can be. And that's how we'll leave it. All right. Number 3, it says, explain why direct substitution does not work for the limit as x is approaching 1 of the function 3x squared minus 2x minus 1 all divided by x minus 1. Does this mean that the limit does not exist? Okay, so why can't we just do a direct substitution here? Do you see a problem with x being equal to 1? Hopefully you've observed that if x is 1 and I substitute a 1 into that denominator, I'm going to have 1 minus 1, which is 0. And division by 0 is undefined. So this means that you cannot get an answer by doing direct substitution, because the denominator would come out equal to 0. The function is not defined when x equals 1. Does this mean that the limit does not exist? So this is a question you may or may not feel confident in answering at this point in time. But if you will recall, last time's lesson when we were doing table method, there were a lot of problems where the limit had x approaching some number, like 0 or whatever, that if you were to substitute it into the function when we made the table, it was undefined there. And there still was an answer for the limit. So we're going to say direct substitution does not work for this because the function is not defined when x equals 1. Does this mean that the limit does not exist? The limit might still exist. So if direct substitution does not work, all that means is that you need to try a different method. It doesn't mean the limit does not exist. Okay, so we're going to look at our next algebraic method for calculating limits, and it is called the factor and simplify method. So on number 4, we have the limit as x approaches 3 of the quantity x squared minus 9 divided by the quantity x minus 3. So, in order to do this, we cannot use direct substitution, because if you substitute the 3 into the denominator, you have 3 minus 3, which is equal to 0. So direct substitution won't work. So our next easiest and best method of choice would be the factor and simplify method. So the denominator of this fraction is already simplified, but the numerator is not. So I'm going to say, well, this is equivalent to the limit as x approaches 3 of the quantity x plus 3 times x minus 3. This numerator is a difference of squares. So we factor a difference of squares by taking the square root of the first term in the front of both sets of parentheses, the square root of the second term in the back side of both of the parentheses, and one factor is positive and one is negative. You can always multiply these two factors back out by using FOIL to double check. It should be equal to what we started with. So that'd be x squared minus 3x plus 3x, so those add to 0, and then minus 9, which gives us what we have here. And this is all divided by x minus 3. Okay, so we did the factor part. The next part is to simplify. We have a set of common factors here. X minus 3 on the top, x minus 3 on the bottom. So those simplify, because any number divided by itself is equal to 1, except for 0. 0 divided by 0 is undefined. But anyhow, now the limit as x approaches 3 of x plus 3 is all that's left. So now it turns into a direct substitution problem. We can just take that 3 and substitute it in where the x is. So it's 3 plus 3, which is equal to 6. The answer is 6. Okay. Now, let's take a look at number 5. We have the limit as x approaches 3 of the x minus 3 in the numerator and x squared minus x minus 6 in the denominator. So can we do direct substitution? Well, 3 squared is 9. Subtract 3 gives you 6. Subtract 6 gives you 0. No, direct substitution will not work. So we are going to factor and simplify. So we're going to do the limit as x approaches 3 of x minus 3 in the numerator is fully factored. And on the denominator, I need to factor this quadratic trinomial. Factors of x squared are x times x. Now I need factors of 6 that subtract to make -1. And I'm kind of guessing, because these problems are designed to work, that one of the factors might be x minus 3 so that these subtract out. If it was x minus 3, the other factor would have to be x plus 2, so that -3 and +2 would multiply to make 6. So, now I've got it fully factored, so I can simplify. And when I simplify in the numerator, the whole numerator was gone. When the whole denominator was gone before, I didn't have to write anything. But that's because this x plus 3 is kind of like it's over 1. Here, when the entire numerator divides out, I have to leave a placeholder of 1, because anything times 1 is itself. If you have a 1 on the bottom, you don't have to write it. But if you have a 1 on the top, you do. So 1 over x plus 2 on the bottom. Finally, it turns into a direct substitution problem. I can substitute this 3 in where the x is. 1 over 3 plus 2 is equal to 1/5 for the answer. Okay, one thing I want to show you about the work that I'm doing. In calculus, you're going to need to show your work for credit. Notice each statement has the limit written in front of the function until I do the direct substitution step. Once I substitute this 3 in for the x, I no longer have to write the limit as x is approaching 3 because guess what? Now x is 3. So the x is gone and it's just numerical. This is the answer to the limit problem. So once you've substituted that value in place of your variable, you no longer write limit on that step. But the other steps should have the limit as x is approaching the value preceding the function. So now for number 6. My recommendation to you is that you pause your video and try this one on your own to see how you do, and then check to see if you got it right. Okay, so hopefully you've gotten it done. You've got a great answer. You're confident in it. We cannot do direct substitution here because if I substituted the 1 in place of the x, 1 squared is 1 minus 1 is 0. So now I am going to factor and simplify. On my numerator, I need factors of 5 that add to make -6. So I've got x here and x here. 5 times 1, I need it to equal a -6, so I want both to be negative. And now in my denominator, I have x squared minus x. These two terms have a greatest common factor of x. So I'm going to go x times the quantity x minus 1. It's kind of like the reverse distributive property. If you multiply that x in, you get x squared minus x. Okay, so now I've done the factor part. And simplify. Are there any common factors among the numerator and the denominator? Yes, x minus 1s are common. Those divide out because they equal 1. So now I've got the limit as x is approaching 1 of the numerator of x minus 5 over the denominator of x. Now I'm ready to do that direct substitution step. And here I have 2 places to substitute in my 1. So this will be 1 minus 5 in the numerator divided by 1, which is equal to -4. Oops. Started trying to draw my box around just the 4 and not including the negative. Whoops-a-daisy. Okay, so hopefully you're feeling pretty good at this point about using both the direct substitution and the factor and simplify methods. We have 2 more methods to learn. So moving on, we're going to do using conjugates next. Okay. For using conjugates, you'll see each one of these problems has a square root in it. So this is going to be a common method that we use to tackle problems that have some oddball square roots laying around in them. Now, for the number 7, can we use direct substitution? If you plug in a 1 in the denominator, it is 1, and that's fine. The numerator, square root of 1 plus 1, that's the square root of 2 minus 1. I mean, that's a number. That's okay. So even though I put this problem in the using conjugates section and it looks like the others that we're going to do using conjugates, you need to be in the habit of checking to see if direct substitution would work first, because if you can use direct substitution, you need to use direct substitution. And this one you can. So we're just going to fill in the 1 in place of both of the x's in the function. So this gives us square root of 2 minus 1, and the denominator of 1 is not needed. So there's our answer. So I didn't actually use conjugates here. I used direct substitution. Okay, now, just as a reminder, keep looking for direct substitution. On number 8, I cannot use direct substitution because I'll have 0 in the denominator and division by 0 is not defined. So on this one, I have to try another method. Would I look to do factor and simplify here? Well, this doesn't look like stuff that I have any factor patterns for. It's not like quadratic trinomials or differences of squares or anything like that I factored in my mathematical prior learning. So that's not a good method here either. So the next step is going to be to use conjugates. You did learn about conjugates. You learned about them when you were studying rational equations, which are or radical equations, equations with square roots in them, and also with imaginary numbers, which by the way are not going to be a topic of study in calculus. But what a conjugate is you're going to take this fraction and you're going to multiply it by a clever form of the number 1, which is something over the exact same thing, something divided by itself to equal 1. And the number that we're going to multiply by is going to be very intentionally chosen. Wherever you see your square root, whether it's in the numerator or the denominator, you're going to go to the part of the fraction that has the square root in it. So this problem, it's the numerator. And you're going to write down the exact same thing that you have here, except for the sign that separates the two terms. This whole first term is under the root, is going to change. So I'm going to have the square root of 4 plus h, and then instead of the minus, I'm going to put a plus here, and then my 2. So change sign and multiply. So we multiply by that over itself. The numerator and the denominator get multiplied by this so that you're multiplying by 1 because we don't change the value of the function. So why did we do this? Well, on the numerator, let's FOIL this out. First term times first term. When you multiply something under a square root by the exact same thing that's under the square root, it causes the square root to be squared, which means all that's left is the argument of the square root, the 4 plus h that's underneath it. The outer term is 2 times the square root of 4 plus h, and the inner term is negative 2 times the square root of 4 plus h, which add up to 0. And that's always going to happen. The outer and inner terms are always going to cancel when you multiply by a conjugate. And then the last term is negative 2 times positive 2, which gives you negative 4. So now we've removed the square root that was bothering us there in the numerator. Now, for the denominator, I'm just going to write h parentheses and then this one. I'm not going to bother distributing it, and it would probably be a problem if I did because I'd have to then go back and factor it out again in the next step, which we don't want to do. So now after I have FOILed out the binomials that had the square roots, where I multiplied by the conjugate, and then just kind of sandwiched together the other part of the fraction with parentheses, so they're multiplied but not actually like distributed. I'm going to simplify that conjugate further if possible. So 4 minus 4 is 0. So now I'm just left with an h on the top, which comes in handy because the h now will divide out and equal 1 with that h that I have on the bottom, and you'll remember that h that was on the bottom was the problem that was causing me not to be able to put the 0 in. So this h and this h divide out to equal 1. Of course, I'm going to leave my 1 in my numerator here. So now, oh, and I haven't been writing, I've been modeling bad mathematics. The limit as h approaches 0, the limit as h approaches 0. Now I'm ready to substitute in the 0. So I've got 1 on the top and the square root of 4 plus 0 under the square root plus 2. So what is the square root of 4? It's 2. 2 plus 2 is 4. So the answer is 1/4. All right. About clear as mud, right? Now we're going to go on to number 9. This is another conjugate problem. If you substitute in the 1 in the denominator, you'll have 0. So we look for the part of the fraction that has a square root. From number 8, it was on the top. For number 9, it's on the bottom. It's in the denominator. So for the denominator, I'm going to multiply by the conjugate of that denominator. So it's going to be the square root of x plus 1, because I'm just changing the sign in the middle and then multiplying by that over itself. So I'm just multiplying by a clever form of the number 1, not changing the value of the function. And now I'm going to be a good mathematician and put the limit as x approaches 1. And I'm going to FOIL out on the part where the conjugates were, which is the denominator. The numerator, I'm not. Oops. X minus 1 times the square root of x plus 1. The reason I'm not multiplying it out on the opposite end is because here it's in factored form, and I'm hoping that probably a factor is going to cancel. So it kind of turns into a little bit of a factor and simplify situation here. Now, square root of x times square root of x is just x. My outer term is positive square root of x. My inner term is negative square root of x. Those add up to 0. And then negative 1 times positive 1 is negative 1. So notice, now I have x minus 1 in both the top and the bottom, which means they can divide out to equal 1. And I can do my direct substitution on my next step and say the square root of 1 plus 1 for the numerator, and the denominator is just left with a 1, so I don't need to put that. Square root of 1 is 1, and 1 plus 1 is 2. Yay for first grade math. Okay, so there's some practice on the using conjugates method. Now we're going to go on and do a method called common denominators. The first example that I'm giving you is probably easier than any that you're actually likely to come into contact with, but maybe just to kind of introduce the concept. The limit as x is approaching negative 2 of x squared divided by the quantity x plus 2 plus 2x divided by the quantity x plus 2. First question, can we do direct substitution? No. If I substitute a negative 2 in here on the denominator, I will have division by 0, which is not defined. So, should I do factor and simplify? Well, x plus 2 is not going to be a factor of the top or the top of either fraction, so no, I can't simplify anything here. So, is this a conjugate problem? Well, there's no square roots, so no, not a conjugate problem. So my next best guess is to use the common denominators method, which means I'm going to combine the fractions. Notice both of these already have a common denominator. That's why this one is kind of too easy. So all you have to do is put the fractions together. So just like a little recap, this is like adding, let's see, 3/7 plus 2/7. You have a common denominator, you just put the numerators together, 3 plus 2 over 7, right? That's what we're going to do. So the limit as x approaches negative 2 of x squared plus 2x, adding my numerators together, over x plus 2 in the denominator. Now, can I do direct substitution? Still no. Can I do factor and simplify? Yes. How does my numerator factor here? Pull out the greatest common factor of x. That leaves me with x plus 2. What do you know? There's an x plus 2 on the bottom. I never saw that coming. So now we're going to take x plus 2 and divide it by x plus 2, which means I'm just doing the limit as x approaches negative 2 of x. All that's left is an x. So if I plug my negative 2 in place of my x, this just equals negative 2. That's the answer. We're done. Woohoo! Okie doke. So next, let's look at number 11. Number 11 has the limit as x is approaching 0 of 1 over x minus 1 divided by the quantity x squared plus x. Should I do a direct substitution here and put the 0 in for the x? No, because this first fraction will come out equal to 0. So I again am going to go with the common denominators method because factor and simplify, there's nothing in the numerator to cancel with the denominator, so that's not helpful. There's no square roots, so conjugates doesn't seem likely. So now I need to get a common denominator and put these two separated fractions together. So they do not currently have a common denominator. I have to make them have a common denominator. This is kind of like adding 1/3 plus 1/6. You would have to first take this first fraction and multiply it by 2/2 to get the common denominator of 2/6, and then you can add them together the same way we did with the sevenths above. So that's the plan. So this factor is here, this denominator is x times x plus 1. And we have the x here, so the missing factor that it needs is an x plus 1 over an x plus 1. So we're going to say this is equal to the limit as x approaches 0 of x plus 1 over x times x plus 1 minus 1 over x times x plus 1. And now that I have a common denominator, I can combine those two fractions by keeping the denominator the same and subtracting the numerators. So the limit as x approaches 0 of x plus 1 minus 1 over x times x plus 1. And then these ones obviously subtract to equal 0. So I'm just left with an x in the top, and that x divides out with the x on the bottom. So my numerator is going to be 1, and my denominator will be 0 plus 1, which means the answer equals 1. All right. Number 12 is a hard one. And you're probably not going to see too many of them like this, but I'm pretty much sure that you're going to see at least a little bit more of this. So, this problem, unlike the last two, are not set up just like two separate fractions. You cannot do direct substitution. Plug in the 2 there on the denominator. 2 minus 2 is 0. Division by 0 is undefined. So that won't work. Factor and simplify. We don't see things that we can factor and cancel out. We don't have square roots, so we do have to use the common denominators method. But it's not quite as basic as the last two. So this is called a complex fraction because we have fractions stacked up on a fraction. And complex fractions show up here and there in math, and generally when they do, they cause issues because they are confusing and people make mistakes with them. There's more than one correct way to do this problem. I will assure you of that. But I will also assure you that one way is easier than the other way. And students tend to gravitate toward the longer method when solving this. So the longer method is to multiply this first fraction times 2/2 and this second fraction times x over x, get a common denominator in the numerator and put those two together first. That doesn't help you a whole lot. So I don't like to use that method because it's going to take longer. It will work. You can get the correct answer that way. And some of you are going to want to do it that way because you feel more comfortable with it. That's fine. But I'm going to show you a way to do the problem that I believe is a little bit easier. So within the numerator, my two denominators are x and 2x. I'm going to multiply those together. So that would give me 2x. And I'm going to multiply this by a clever form of 1, that being the product of those two denominators within the numerator over itself. So I got my 2x from these two multiplied together. And I'm multiplying by a clever form of 1, 2x over itself. Now, I'm going to distribute this times both of the fractions in the numerator. So this is going to be the limit as x approaches 2. So this first fraction, when I multiply it by 2x, it's like it's a 2x over 1. 2x over x, the x's cancel, and I'm left with 2. Then I have my minus 2x times a half. It's like 2x over 2. The 2's divide out, and I'm left with x. And then in the denominator, I'm just going to put x minus 2 times 2x. Just sandwich them together with parentheses, not distribute them out, because I'm trying to make something cancel. This x minus 2 is the factor that's causing me to have the problem with plugging in that 2. So it's the one I would ideally like to get rid of. And now I can see that I have almost the same factor in the numerator, except for everything's the wrong sign. My 2 is positive here and it's negative down here. My x is negative up here and it's positive down here. So do any of you know a clever way to change that top fraction so that both the signs change? Maybe we could factor out a -1. Sneaky, huh? If I pull the -1 out, like reverse distribution, this 2 would become a -2, because when you multiply that -1 times that -2, you'd have that positive 2. And this negative x, if I factor out the -1, would then be a positive x, because multiplying that -1 times that positive x gives me that negative x there. Which now is equivalent to x minus 2, because -2 plus x is the same thing as x minus 2. I mean, if you want to write it that way, we sure can. It's not necessary to do so. -1 times x minus 2 over x minus 2 times 2x. So my x minus 2's divide out, they equal 1. And now I have the limit as x approaches 2 of -1 on top and 2x on bottom. I can now do my direct substitution, -1 over 2 times 2, which is -1/4. Okay, so still not a short problem. Complex fraction problems usually aren't, but a little bit easier than had we combined our numerators and then proceeded from there. Okay, so we have learned 4 different methods of solving limit problems algebraically. In our next problem, number 13, I'm going to give you 4 limit problems, and I'm going to ask you to figure out which method you would solve each one with: direct substitution, factor and simplify, using conjugates, or common denominators. And then how did you know you should use that method, and how do you calculate those limits? So I'm going to show them to you, and then I'm going to have you pause the video to work them out. So let me see. This paper is landscape, and my camera is not quite wide enough to show you all of them at the same time. Let's see if I can raise it up a little bit. There we go. Okay, so you might want to pause your video right here and try to do this on your own. Okay, hopefully you're coming back after having paused it, and I can go through these with you. So, which problem, A, B, C, or D, was the direct substitution problem? It was D. And how do you know? Substituting in the number that x is approaching doesn't cause division by 0. Okay. How about factor and simplify? Which one was factor and simplify? Did you get A? I bet you did. We have a problem where direct substitution won't work. but we do have factorable polynomials in the numerator and the denominator. All right, conjugates method. Which one's the conjugates method problem? B. I bet you got B. Direct substitution won't work. And I see a square root. Okay, common denominators, C, because of the process of elimination. No, that's not a good answer. Direct substitution won't work. But we do have separate fractions. So putting those together is our best bet. So now, what about the answers to those? Did you calculate the limits? Hopefully you did do so. And hopefully you got these answers. -4/5, 4, 4, and 15. All right, number 14. The limit as x is approaching -2 of x cubed plus 8 divided by the quantity x squared plus 2x. So, how do we do this one? Well. Is it direct substitution? Let's see, -2 squared is 4, and then -2 times 2 is -4. 4 and -4 makes 0. Nope, not that easy. So the next thing we would consider is factor and simplify. Are these polynomials in the numerator and the denominator factorable? Why, yes, indeed they are. And how do they factor? Well, because we're amazing at algebra, we all remember the sum of cubes pattern, right? Maybe not. It's okay. I know. Y'all don't do that much in Algebra 2 or in pre-cal, so it can be challenging to remember. If you remember it, that's great. Just write down the factors in the numerator. If you don't, I'm going to give you a backup plan. And that backup plan is one that students use a whole lot more in algebra and pre-cal, and you probably do remember how to do that. That is synthetic division. First of all, you can probably guess one factor of x cubed plus 8. The cube root of x cubed is x, and the cube root of 8 is 2. So x plus 2 is a factor. That works every time. But the other factor is a quadratic trinomial, and it's harder to come up with if you don't remember the signs and the products and all that. So I'm going to do synthetic division with the coefficients from x cubed plus 8. So the coefficient of x cubed is 1. There is no quadratic term, so I have to put a placeholder of 0. There's no linear term, so I have to put a placeholder of 0. And then 8 is my constant term. And the number I'm dividing by is whatever I get when I set this factor x plus 2 equal to 0 and solve. So you'd subtract 2 on both sides, and you divide by -2, basically the opposite sign of the factor. So you bring down the 1, and then you multiply diagonally. 1 times -2 is -2. Then you add vertically, so that adds to -2. Multiply diagonally, 4, add vertically, 4, multiply diagonally, -8, and add vertically, 0. That last number is your remainder, and that remainder should be 0 if it works. So it did work, and this gives you the coefficients for your other factor. So this is the constant term, the linear term, the quadratic term. So this is x squared minus 2x plus 4. Some of you might have remembered that this was this is called a and this is b. This is a squared minus the product of a and b plus b squared. That's the factor pattern for the sum of cubes. But like I said, there's your backup plan. Use the synthetic division to get the other factor. Now our denominator has a greatest common factor of x, and if you pull that out, you're left with x plus 2. So we have a common factor of x plus 2 in the numerator and the denominator, so we can simplify that out. And at that point, we're ready to use direct substitution. Watch when you're subbing in a negative number because the negative needs to be squared along with the 2. Minus 2 times negative 2 plus 4 all divided by negative 2. So this is positive 4 plus 4 plus 4 divided by negative 2. So 12 over negative 2 is negative 6. Okay. We just have one problem left to do on algebraic methods of solving limit problems. This is a piecewise defined function. If f of x is equal to 3x minus 1 for x values less than 3, and x squared plus 1 for x values greater than or equal to 3, determine the limit as x is approaching 3 of the function f of x. Oh my goodness, Mrs. Heiss, how do we do a piecewise function? There's too much math here. It's okay. It's not that bad. What is always the first method that we try? Direct substitution. Now we want x to equal 3. So we would need to plug that 3 in, directly substitute that 3 in to both pieces of the piecewise function because 3 is the point where we switch from one to the other. And we need to get the same output on both to say that that could just be the limit. So let's try it. In the top piece, 3 times 3 minus 1, that's 9. Take 1 away. That gives me 8. Okay, let's substitute 3 in for the x in the bottom piece. 3 squared plus 1. That's 9 plus 1 is 10. Are they the same? No, they are not. That means the limit as x approaches 3 from the right side of the graph, where the x values are bigger than 3 of f of x, is not equal to the limit as x approaches 3 from the left side of the graph, where x is smaller than 3 of f of x. So that means that the limit does not exist. Okay? Oops. There we go. The left-hand limit and the right-hand limit are not equal to each other, so the limit does not exist. Now, what if this was not x squared plus 1? What if this was x squared minus 1? Then we'd have 3 squared take 1 away, which would be 9 minus 1, which would be 8. They would be equal to each other, and direct substitution would work just fine, and you could say the limit does exist, and the answer is 8. Okay? So, or if this 3x minus 1 was a 3x plus 1, then it would be 9 plus 1, which would equal 10. And both the left and the right-hand limits would be equal to the same thing, and you could say the limit exists, and it is equal to 10. So, that wraps up our algebraic methods of calculating limits. Please do not use a calculator for any of your practice problems on this lesson, because if it was a calculator problem, you could do tables or graphs like last time, and that would not be the method we're trying to work with today. We're trying to work with algebraic methods. Of course, feel free to use a calculator if you want to check, but as you're working, see if your answer is reasonable, but try to do it using the methods we learned today. I hope you have an absolutely wonderful day, and I look forward to seeing you soon. If you have any questions, please do not hesitate to reach out to me. Send me an email, let me know. I'd be happy to help in any way that I can. Have a great day. Bye-bye.